So we just finished up with our introduction to momentum. So I wanted to today is right now talk about collisions in one dimension. And if you see this, which we sort of went over in class today, I'm actually just going to upload this because I couldn't exactly get it onto the video and into the Smart Notebook. But I'm just going to upload the solution set so you can sort of take a look at it. But I can give you some slightly different examples, and then you can sort of get into what's going on with this. And ultimately, I'm going to do some simple collisions in one dimension, and then I'm going to have you look at the last problem of this, which even though it's sort of on the two-dimensional page, it's this one down here with a ball inside a potato cannon. It's actually a one-dimensional problem too. So hopefully by the end of this, you can attack the first page, and then the second page, and then number 8, which is the bottom of the third page. So let's talk about collisions in one dimension. The first thing you got to remember is the big rule about momentum from the last video, which is that momentum is always conserved. So P total I equals P total F. So I typically, whenever I see a momentum problem, I'll always sort of draw a little squiggly line and split it in half. And before literally means before these two objects collide, what's happening? And after signifies that after these two objects had collided, what's happening? So I think the first thing, the easiest collision to look at in this scenario is going to be a perfect inelastic collision, or a PI for short. So I'm going to go through the three types: a PI, perfect inelastic, an NI, a normal inelastic, and a PE, a perfectly elastic collision. And the methodology is the same for all three, and I'm actually not even sure if I'm going to bother with all three because you only need to know how to do two of them, because perfect inelastic is different than perfect elastic and normal inelastic. So I think I'm just going to do two, and then you can probably figure out how to do normal inelastic and perfect elastic together. But let's just take a scenario that let's take our Julian Edelman example again, and let's say I'm going to run after him and tackle him. That should be fun. So let's see. Here's me, Mr. D, and here's Julian. All right. Now let's say I'm running at Julian, and let's say Julian has a mass of 100 kilograms, and his velocity is 0. Let's say I'm running at him, and for argument's sake, let's say my mass is 130 kigs, and I'm running at him at 5 meters per second. So I'm pretty quick at him. Before the collision, we should probably know what the momentums are. And we say P total I, so we got to look at the total momentum of both of us before the collision. So in order to get my momentum, we need to know my mass, which is 130, times my velocity, which is 5, plus we need to know Julian's momentum, which is 100 times 0, and we got to get the total. So 130 times 5, I have no idea, but I will tell you in a second. 130 times 5, that would give me a momentum of 650 kilogram meters per second. And Julian, well, even I can do this, 100 times 0, he's not standing anywhere, and he's going to have a momentum of 0 before I run into him. So, cool. My initial momentum before the collision is 650 kilogram meters per second. I'm going to move this down because it is very crowded here. Go away, Julian. Go away, perfect inelastic. Okay. So the total momentum before I run into him for both of us is 650 kilogram meters per second. What that what the law states is that we have to have the same momentum after we collide. So we know that whatever momentum we have after our collision is also going to be 650 kilogram meters per second. So I'm actually going to put that here. So equals 650 kilogram meters per second. Well, what equals 650? Well, both of our momentums. So the momentum of me, momentum of D, plus the momentum of Julian Edelman. But if you remember, I said that this is going to be a perfect inelastic collision. And what that means, and what that should set off into you, is an alarm that says, well, wait a minute. These two people stick together. So what's going to happen to our mass and our velocity? It's not that there are two separate things anymore. Now we're one thing. And our masses have combined, and we are going to be moving at the same velocity. So what you need to figure out is, well, what's the new mass? And I'm going to give you a second because you can do this in your head, I hope. My mass, which is 130 kilograms, and Julian's mass, which is 100 kilograms, should give us a total mass of 230 kilograms. And what we're going to do is we're going to figure out what our new V is. Now, first off, I want you to remember that I made a big deal about the fact that momentum is a vector. The fact of the matter is this 650 is positive. And I evidently am running positive 5 meters per second, which means I'm running this way to the right. Julian's standing still. So if I run this way to the right and I hit Julian, we're both going to go to the right. And we can figure out how fast we're going to go by figuring out that V. And that's typically what we'll ask in one of these momentum problems. We'll ask you what the final velocities are after a collision has happened. So we can do this kind of math. This isn't terribly hard. We're going to solve for V, knowing that we're going to divide both sides by 230. Divided by 230. Divided by 230. And let's see, 650 divided by 230 should give us approximately 230. Should give us about 2.82 meters per second. Now, very interesting. It means we're both going to be going off sort of in this direction at 2.82 meters per second. What if I was running backwards at Julian? So let's say instead of being on this side, I was on the other side and I ran to the left. Well, that means my velocity would be negative, which would mean this would be negative, which would mean this would be negative, which would mean this would be negative. And what that would mean is instead of us carrying off to the right after the collision, we would actually both be carrying off to the left because that negative sign indicates that it is a negative direction. And we're going to come back to that with our next problem. But in a perfect inelastic collision, you're going to have both objects stick together. And after the collision, you are going to know what the new mass is. And that's kind of an important fact. I'm always going to tell you something about what happens after the collision. And in this case, what I told you about after the collision is sort of what you have to infer. That the mass, if I tell you what kind of collision it is going to add together. Now, in another kind of one-dimensional collision, let's say, I don't know, let's keep this a little easier than people because I'm not good at drawing. Let's say I got a marble going this way, and let's say I have another marble going this way. And let's say they collide. So let's say this marble has a mass of, I don't know, 5 kilograms. Let's say it's a big marble. And this marble has a mass of 4 kilograms. And let's say the first marble has a velocity of positive 5 meters per second. And let's say this marble has a velocity of negative 3 meters per second. Cool. Then they collide. 4. And let's say afterwards, and let's make this a little easier, I'm going to make this second marble, let's make this red. So I'm going to have a black marble and a red marble. Okay, let's try and make this a little easier for all of us. Let's say that after the collision, the black marble proceeds forward at a half meter per second. I want to know, after the collision, what does the red marble do? Okay, just for argument's sake. Now, before I even get into the math, with the previous example, we had a perfectly inelastic collision, which means before the collision, there were two of us. After the collision, essentially, there was one of us. And we know something about after the collision because we know the new mass. With this, I have to tell you what one of the balls is doing. And we'll see why in a second, but that is a very, very big deal. And this could be either a perfectly elastic collision or a normal inelastic collision. So it really doesn't matter because you solve it the same way. The only difference is if you did 1/2 mv squared with a perfect elastic collision, before the collision you would have the same number of joules as you do after the collision. And with a normal inelastic collision, you'd have some number of joules before the collision and then you'd have fewer joules after the collision. But I'm not going to make you sort of look at that. That's more of an AP thing. So for right now, just hang out with just dealing with the momentum. So before the collision, I want you to figure out the momentum of the black ball, and I want you to figure out the momentum of the red ball. And I'm actually just going to draw a little, not that. I'm going to go ahead and draw a little black marble here, and a little red marble here. And then I'm going to draw another black marble here, and I want to draw a little red marble here. And I want you to put underneath, or on your paper, or whatever, however you're looking at this, what the momentum of the black ball is going to be, what the momentum of the red ball is going to be, and then we'll look at what happens after the collision. So, in your infinite wisdom, 5 times positive 5 should give us positive 25 kilogram meters per second, black ball, before the collision. And for the red ball, 4 times negative 3 is going to be negative 12 kilogram meters per second. And this is why I said originally that momentum is a vector. The positive means it's going to the right. The negative means it's going to the left. So if we add 25 and negative 12, we should get a grand total momentum going into the collision of positive 13 kilogram meters per second. Okay, and I subtracted, I added these two together, 25 plus negative 12, or I subtracted 12 from 25, however you want to do it. But you should get a P total I of positive 13 kilogram meters per second. What does that mean the total has to be after the collision? And I hope you are going to say P total F also has to be positive 13 kilogram meters per second. Okay? Fine. Not too complicated yet. That's just the rule of conservation of momentum. Well, what you don't know is how you're going to break that 13 kilogram meters per second up between the black ball and the red ball. And that's why I said before, I have to tell you what one of these balls is doing. So what I tell you is the black ball is going 0.5 meters per second to the right, and we have a velocity, a mass still of 5 kgs. We haven't changed the mass. These two balls haven't stuck together. They're not made of clay and going squishy. They're two marbles. So they're going to bounce off each other. We know the momentum here is the mass times the velocity, which is the mass is still 5. The velocity is now 0.5. So its momentum is positive, because it's positive 0.5 meters per second, positive 2.5 kilogram meters per second. And that means the red ball has to be doing whatever's left to get it to be 13 kilogram meters per second. Well, how do we figure that out? You subtract 2.5 from 13. Because if you know the total is supposed to be positive 13, and you're already 2.5 there, what do you need to make up the rest of it? And the answer to that should be 10.5 kilogram meters per second. So last time I checked, unless my math is no good, 10.5 plus 2.5 gives me 13. Cool. Well, now I want to know what the ball's doing, but I know its momentum. But if we know its momentum, that equals its mass times its velocity. Do we know the red ball's mass? Yup. Do we know the red ball's velocity? No, but we can figure that out because we know the total momentum. So 10.5 equals the mass 4 times the velocity. And to solve for the velocity, we divide both sides by 4. And our velocity will be, interestingly enough, a positive number. 10.5 divided by 4 should give us 2.625 meters per second. I hope that makes sense for the logic. And, we're all looking for how do we do this? What's a good way to set this all up? In my mind, it's the easiest thing to do just to keep everything separate. We know what's happening before. We know what's happening after. And I said above, I sort of just split it up in half. And if I know what the total momentum is before, and I know what the total momentum is after, I can pretty much figure everything else out. Okay? But the same deal, you would do the same thing whether or not it's a perfect elastic or normal inelastic collision. So the last one that I want to talk about, and this is what's going to eat into a little bit more time, but I'm okay with that. This is sort of the opposite. We have a before and we have an after. But this is a very unique situation because this is what we call an explosion. Which means it is a perfect inelastic collision run in reverse. Remember, in a perfect inelastic collision, you have two objects that smack together. In an explosion, you have a smack together object that breaks apart. So before, we're going to have two things that are stuck together, and after, we're going to have two things that are unstuck together. What I mean by that is, take a look, and forgive my bad drawings. Potato cannon, potato. A 0.25 kilogram potato is fired from a potato cannon with a speed of 60 meters per second. What's the recoil speed of the 5 kilogram potato cannon? Well, here's the potato, here's the cannon, and let's say the potato gets shot out that way. Fair? I hope so. And if not, I don't care. So, what we know is the mass of the potato is 0.25 kigs. We know the mass of the cannon is 5 kigs. And we know before it's even fired, the velocity of both should be 0. So the momentum total before the collision, mass times velocity, it's all just going to be 0. Well, if that's the case, what does the momentum total after the collision have to be? You guessed it, 0 meters per kilogram meters per second. 0 kg meters per second before, 0 kg meters per second after. But how is that possible? We have an explosion. Well, it's actually pretty simple. After the explosion, your potato is going this way with a velocity of 60 meters per second. Right there. And because I drew it backwards, it's actually a velocity of negative 60 meters per second. And the mass isn't changing, 0.25 kilograms. And what I want to know is, what's the potato cannon going? Well, if the potato is going to the left, the potato cannon must be going to the right, because that's the only way you can get things to cancel out equal 0. And if you're not sure about that, well, okay, fine. P equals mv, P equals mv. Well, what's the momentum of the potato? 0.25 times negative 60 plus 5 times something. But it all has to equal 0. So I'm going to move this guy down. 0.25 times negative 60. 0.25 times negative 60. 0.25 times negative 60 equals negative 15. So, 0 equals negative 15 plus 5v. Now here's what I want you to remember. In the problem it says 60, but it actually says speed, so I don't really tell you which direction it's going. It could be positive 60 meters per second, it could be negative 60 meters per second, but you guys need to make that decision. But it doesn't really matter, as long as you keep track of what your positives are and what your negatives are. Because now I'm saying, okay, I've got a negative momentum for the potato, so that means I'm going to have to have a positive momentum for the potato cannon. How do I get rid of this negative 15? I add 15 to both sides. So positive 15 equals 5v. Divide both sides by 5. Divide both sides by 5. My velocity for the cannon will be 3 meters per second in the positive direction. So, cool. What if I flipped it? Well, then the potato would be going in the positive direction and the cannon would be going in the negative direction. And you would just have the different sign, but the same magnitude. You'll always get 3 meters per second. It's just a matter of if it's positive or negative. Okay? So the convention is kind of yours. It's however you want to handle each problem. Unless I specifically say, you know, this velocity is negative something or this velocity is positive something. You can kind of choose your own adventure with these. But that's how you look at the last problem in the problem set that I gave you guys on Friday. Okay? I hope this makes sense. I hope this explosion makes sense. And it's very cool. Again, it's just one dimension, so it shouldn't be that terrible and scary. Okay? I hope this helped you a little bit more. And now it's time to move into momentum in 2 dimensions.